Hello, welcome to another video on 3D modeling in Creo. We'll continue our discussion on putting together parts, individual parts in 3D assembly. Previously, we made a gear train uh, like this, but that gear train was not movable because the connections that we used did not allow for movement. But now we've learned how we can make movable joints. For example, this gear that we have that is connected using a pin joint, and that allows for the gear to be rotated about its axis. Right now, we can't rotate it beyond this 180-degree limit because of constraints that we've put. But if we get rid of those constraints, we can rotate it an entire revolution. And what we'll do now is to add a gear, an identical gear in this case, on the second shaft. And I've placed the second shaft at a distance equal to the pitch diameter of these gears, so that the pitch diameters of the two gears would be tangent. And then we'll apply rules of mechanics, whereby when we move the driver gear, the driven gear would move corresponding to the gear ratio, and the speed and torque would be transmitted accordingly. So let's import another copy of this gear. Similarly to how we've done it in the past, I'll import it, and I'll add this gear to this shaft using a pin connection. As we've discussed, the first thing that you need to define while defining a pin connection is the axis. So I selected the axis of the shaft, and then I selected uh, the central axis of the gear. And the second thing that we need to define is the constraint that limits motion along the axis that we've just defined, because the gear can still translate. So we'll select a planar object on the assembly and a planar surface on the gear, and then we'll select a constraint that fits our requirements. In our case, we want it to be at a distance, so I'll have it at a distance here. I think this value should be 1.5 if I wrote it correctly, and in that case this gear should be in the same plane as the second gear, but we can verify that very quickly by looking at it perpendicularly from here, and both the gears are uh, on the same plane. And both the gears have been defined using pin joints, so we can move them. So this gear moves completely. By the way, I'm moving this by pressing down Control and Alt and clicking the left mouse button, and that's equivalent to using the drag component tool. So this gear can move completely, and this gear can rotate as well, but not completely. So what we'll do is that we'll get rid of those additional constraints, limits to its rotation that we prescribed previously. So you see over here we've prescribed minimum and maximum limits. If we get rid of these limits, now this gear is capable of moving freely as well. But what we want is to make our assembly respect the laws of physics, where what it's doing right now is not possible. So let me hide some of the datums. Right now what's happening is that these gears are moving through the other gear, and they're not respecting the fact that you can't just push through matter, push through solid. What we want to do is to apply the laws of physics, where when we move this gear, the second gear should move as per the gear ratio in between. So before we do that, let's place our gears in their starting position. So I'll look at it perpendicularly from here. Sorry, from here. Look at it perpendicularly from here, and zoom in on the meshing gear, the meshing tooth. So this tooth is the one which is currently being fully engaged. So we want to have it just barely touch, not the most scientific of ways. You could be more thorough and have uh, curves be tangent to each other, and you could prescribe that, but this is good enough for what we are trying to do, so it's not worth the extra effort. You could verify this by going to analysis and looking at the interference as well. So if this is where we're starting from, now let's prescribe those laws of mechanics so that moving one gear will move the other gear. You go to applications, and within applications, there is a sub application of PTC Creo known as PTC Mechanism, and that's what we need to define that gear relationship. And if you see over here, there are different types of connections here. CAM connections, we're not going to discuss that, but you're welcome to explore those. They're not very difficult to implement. There are 3D contacts, belts, and gears. We are interested in gears. So when you're defining a gear pair, naturally the first thing that you'll define is the first gear, and you identify the first gear not by the solid, but by its axis of revolution. So for gear 1, define its motion axis. This is the first gear's axis. I've selected that, and it's picked up on that. And then you have to define its pitch diameter. For this case, the pitch diameter is 3 inches. I know that, so I'll enter that and I'll click apply. Those satisfy the requirements of gear 1. Again, for the second gear, we'll define its axis of rotation, and then we'll define its pitch diameter, which is 3 inches, again, because they are identical gears. And we'll click apply. In properties, you have to define additional property of your gear set. One thing that we did not define in the beginning was what kind of gear do we have. You could continue with generic, which is good enough, but since we know that our gear is a spur gear, select the gear type to be a spur gear type. And then for spur gears, and Creo considers helical gears as a variant of spur gears, which is not completely wrong. They are spur gears, but with their teeth at an angle. That's also the options for helical gears are also available within over here. But a helical gear is nothing more than a spur gear is nothing more than a helical gear with a helical angle of 0. You will keep this at 0, and since we made this gear ourselves, we know that the pressure angle is 20 degrees. So incidentally, that's what we want. But if you import a gear from an online database, make sure that you know what the pressure angle is, because you'll have to define that over here. And you could manually prescribe the gear ratio as well, but you shouldn't have to, because it knows the pitch diameter and it can calculate it from that. In how you will use gear, you will use the first option where the pitch circle diameter determines the gear ratio, and over here d1 over d2 3 by 3 is 1, so the output speed would be the same as the input speed. That's everything I needed to define. I'll click OK. I can close out from this mechanism application, and now when I rotate a gear, the second gear rotates as well. And you can look at the meshing. One tooth meshes after another, and if you were to compare the input speed to the output speed, which is something that we learn to do later, you'll see that they are the same. The angular velocities, they are the same because the gear ratio is 1. Play around with this. I'll encourage you to pair different sized gears and see if the speed of the output gear is different, and is it respecting is it what you would have expected based on your gear ratio calculations. So this is how you can make a movable gear train